Hello, grade 10. So today we're going to be talking about potential energy. Potential energy is stored energy. And when you store energy in an object, that means the object has the potential to do work. So the object will have potential to do work because energy is the ability to do work. So there are there's multiple types of potential energy. We are going to be focusing or talking about 3 types of potential energy, and then we'll go into detail on the last one. Okay, so one form of potential energy is chemical potential energy. Chemical potential energy is the energy stored in the bonds. Chemical potential energy is stored in the bonds of compounds or molecules. So, for example, hopefully you had some breakfast this morning, or maybe you've already eaten your lunch, and you had some food. And your food contains glucose, and glucose is the basic form of, or kind of the unit form of energy that we can consume. And when your body digests it, it's going to take that glucose and break it up to make other compounds, and in that process, it'll release the energy that's in the bonds. Also, gasoline would be another way that we use chemical potential energy. So gasoline or diesel or methane, all those different types of hydrocarbons that we use as fuel, they have energy stored in their bonds. And when we burn them or combust them, we break them apart and we release that energy. The second form of potential energy is elastic potential. Elastic potential energy is stored when an object's shape is changed. So it's stored when an object is compressed. So we're changing the shape of it. So is compressed or stretched. So for example, a rubber band. Or a spring. So if you take a rubber band and you pull it, you have all that energy stored because you've changed the shape of it, so you've stretched it, and then when you release it, the rubber band then starts to move. So now it's doing work. We're releasing that energy. Okay. The third type of energy is the type of energy that we are going to be looking at in greater detail, and that is gravitational potential energy. So gravitational potential energy now is the stored energy in an object based on the object's position above the Earth's surface. So it's the stored energy based on the object's position above the Earth's surface. So the higher we raise an object above the Earth's surface, the more potential energy it is going to gain. So based on its position above the Earth's surface. So if you were to take your eraser and you pick it up, or anything, right? If you pick up anything in your hand and you raise it above the Earth's surface, if you release it, it would then fall back to the Earth's surface. And therefore, we're releasing all of that gravitational potential energy. Before we go into more detail about gravitational potential energy, we need to discuss mass versus weight. So your mass versus your weight. So mass is represented by the letter little m, and this is a scalar quantity. And this is just how much matter is in an object. Or an object contains. So that is your mass. It is scalar. How much matter is in an object. Your weight now is a vector quantity, and a lot of times we interchange mass and weight when we talk about it here on when we're talking just kind of in general terms. But in science, they're two very different things. Because weight now, if you take a look, we put an arrow over top of it, and that means it's a vector. And weight represents the pull of gravity on an object. So now we've got a pull, so now we've got direction, and gravity is always pulling us to the center of the Earth. So now weight becomes a vector quantity. So the pull of gravity on an object. And the equation for weight is equal to m times g. So your mass times this value now called g. And g is the acceleration due to gravity. So g represents the acceleration due to gravity. So on Earth, g is equal to 9.81 meters per second squared. So basically, anywhere on Earth, at the surface of the Earth at least, when you release something, it's going to accelerate at 9.81 meters per second squared. So for every second it's falling, it'll gain 9.81 meters per second in terms of speed. Okay. Remember mass, we've already talked about mass. We've used this one before. Do you guys remember what the unit of mass has to be? We're always measuring in kilograms. So we use that with our force equation. Okay, so we're going to turn to workbook page 39, and we're going to do a couple examples on weight, and then we'll come back and talk more about gravitational potential energy. Okay, so let's take a look at workbook page 39, example number 1, calculating weight. So again, for all of these, we are going to be writing down what we know. So we're going to calculate the weight of a 65 kilogram woman here on Earth. So we know that the mass of the woman is 65.0 kilograms. And because we're on Earth, the acceleration due to gravity is 9.81 meters per second squared. And it's going to be pointing down. So the direction will be down. So just so we know, it is a vector quantity when we talk about weight. So we want to solve for weight as our question mark, and the equation for weight is m times g. So we're just going to plug in our number. So mass is in kilograms, so we can keep it at 65. Our acceleration is 9.81, and it's meters per second squared, so we just plug it in. If you plug that into your calculator, 65 times 9.81, what do you get? and you should get 637.65 newtons. So we're going to round to 3 significant digits. So both of our values have 3 significant digits. So the final answer for our weight will be 638 newtons. I'm not going to have to ask you for direction, but your weight is always pointing down. Okay, the next example now wants to know if that same woman traveled to the moon, calculate her weight, and they're telling us now that we're on the moon, so they have to give us the acceleration due to gravity on the moon, and that is 1.6 meters per second squared down. So again, write down what we know. The mass of the woman is still 65.0 kilograms, because that does not change when we go to a different planet. But the acceleration due to gravity does, and that's 1.6 meters per second squared. Again, we're calculating weight, so that's our question mark. So now our weight is equal to m times g. We're going to plug in our values, 1.6, oh sorry, mass is, well, it doesn't really matter which goes first, but we'll put 65 in first, and then 1.6, and our units are right, kilograms and meters per second squared. If you calculate it, it comes out to 104 newtons. We are going to round to 2 significant digits now. So take a look. 1.6 is 2 significant digits. So I'm going to pick my first 2 significant digits, which is the 1 and the 0. So now it's going to become 100 newtons is what I'm going to round to. But I can't keep it at 100 because that's 3 significant digits. So now I'm going to put my weight as my final answer as scientific notation. 1.0 times 10 to the 2 newtons. Okay, let's head back to our notebook and we're going to take a look at how we actually calculate gravitational potential energy. So the formula for gravitational potential energy, or sorry, let's first go symbols. So the symbol for gravitational potential energy is EP for potential energy, and then if you like, you can put a little g, or you can just leave it as EP. The unit for gravitational potential energy is a joule, because energy is measured in joules. And the formula that we use for gravitational potential energy is gravitational potential energy is equal to the mass times the height times the acceleration due to gravity. So mhg, or some people write it mgh. Just doesn't matter the order, as long as you got mass times height times acceleration due to gravity. Okay, so we have a new variable here that we haven't written down before. That's height. So how high off the ground are we? And that's got to be measured in meters. So you always have to convert it to meters. Okay, let's give 2 examples a try, and then I'll give you some time to practice on your own, and then we'll come back and talk about kinetic energy. So gravitational potential energy, we're back on page B39. Let's try our first example together. So a 5 kilogram box is lifted by an upward force of 3.75 meters above the Earth's surface to the top of the table. What is the potential energy stored in the box at this new position? So always write down what we know. Mass, 5.2 kilograms. It's lifted by an upward force of 3.75 meters. That's our height. They want us to figure out the potential energy stored, so EP, gravitational, and we're on Earth, so the acceleration due to gravity is 9.81 meters per second squared. Okay, so EP, G is equal to M times G times H. All we have to do is plug in our values. 5.2 times 9.81 times 3.75. We didn't have to convert any units. And so now, plug that into your calculator. You get 191.295 joules. And then we have to look at significant digits. The least number is 5.2. So we're going to round it to our first two digits, the 1 and the 9. So this is going to become 190 joules. And again, we have three significant digits, so we're going to convert to scientific notation. So our potential energy is now going to be 1.9 times 10 to the 2 joules. And that would be our final answer. So again, when you're doing a short answer, just make sure, show me all your work to the end. And if your rounding's a little bit off, or you're not using the proper scientific notation, you're not going to lose a ton of marks. Okay, let's try one more, and then you guys can work on the next set of problems on B40. Okay, the mass of a diver is 55.0 kilograms. And they are standing on a diving platform, and they have a gravitational potential energy of 5.4 times 10 to the 3 joules. What is the vertical height of the diving platform? So we have the mass, and they're giving us now potential energy, or gravitational potential energy. 5.40 times 10 to the 3 joules. They want us to solve for height. So remember, G on Earth is 9.81 meters per second squared. So now we are going to have to manipulate our equation. So let's write out EPG is equal to M times G times H. We are trying to solve for H. So we want to isolate the H. So right now the operations are multiplication. So if we take the right side and divide by M times G, the M and G are going to cancel on the right. But we did that to the right side, so we also have to do it to the left side. So now the formula for height becomes the potential energy divided by M times G, and we're going to make sure we bracket that in our equation in our calculator. Okay, let's plug in the values. So 5.40 times 10 to the 3 joules. And we can leave units out. We're going to divide by 55 times 9.81. So make sure that goes into your brackets in your calculator. Use your scientific notation key to put the 5.4 in. And if you plug that in, you're going to get 10.008 meters. We're going to round to 3 digits. So the height of the diving platform is 10.0 meters. So it's a 10-meter diving platform. Okay, so we're going to stop the video here, and we're going to take a few minutes and try and do as many of the problems on page B40. And then in a little bit we'll come back and we'll talk about our other form of energy, which is kinetic.